let us do one proof. I have promised you that in this class we will not do too many proofs, but we will do some, very few. So, let us do one proof, and the proof that I am going to do today is the proof of optimality of tree A star. So, the statement is that if my H is admissible, then whenever A star removes goal from the fringe, we would have found the optimal path. So, now for the next 10 minutes we are trying to just look at how to prove optimality for A star algorithm when the heuristic is admissible. So, if the heuristic is admissible, and let us suppose that we are about to remove G2 from the fringe. G2 is one of the goals, one of the goal nodes. So, we believe that the algorithm should now finish and we have found the optimal path. But of course, let us say that it is not really the optimal path. That means there is another path which is the optimal path, and if it is another path, it would have its own goal node because it is tree search. So, let us say the optimal goal node that we are looking for is G, and either G may be in the fringe or some other node to that path has to be in the fringe at this point in time. Okay. So, let us make sure that we are comfortable with this setting, right. We have a start node S, we are about to remove G2 from the fringe, G2 is in the fringe, we are about to remove it, we have found, we believe we have, the algorithm should stop now, and we have found an optimal path to the goal. And let us suppose we have not. If we have not, that means we are looking for a different path, and if we are looking for a different path, then it has to differ at some point, and whenever it differs, it will create its own nodes. Therefore, the goal node that we are interested in is a different goal node. Let us say the goal node that we are interested in is G, but we are about to remove G2. Now, if the goal node that we are interested in G is G, that means there is some best path from start to G, there is some optimal path, right, that is some path from start to G. Let us say that path is this one on the in the diagram, and let us say that we have to have some node in the fringe that leads us to this goal. Let us say that node is N. Okay. But we chose to expand G2, we chose to remove G2 and not remove N. So, if the algorithm was right, it should have removed N, but the algorithm tried to remove G2. That means, for whatever reason the algorithm thought that G2 is the right node to remove, that means its F value was less than N's F value. Okay. So, let us first see what we can prove about things. So, the first thing is G2 is a goal, that means its heuristic function is 0, that means its F value is same as its G value. That is a simple thing we can say, F of G2 is equal to G of G2. The second thing we know is that there is a contradiction, it is not the optimal goal. If it is not the optimal goal, that means G of G2, right, the path from start state to G2 is greater than path from start state to goal. That means that G of G2 is greater than G of G. So far so good. Now, if we look at G, if we focus on G, what can we say? Well, we can say that it is also a goal, so its H is also 0, that means its F is equal to its G. Okay. And moreover, because G of G2 is greater than G of G and F of G2 is equal to G of G2 and F of G is equal to G of G, therefore, we can combine these three facts to say that F of G2 is greater than F of G. We are not saying much here, we are basically saying that the F function for G2 is greater than F function for G, because we have assumed that G2 is not the right goal and H's are 0 anyway. So, that is so far so good. Okay so far? Okay. So, now we are going to focus on N, right, because this is the node in the fringe that we chose not to expand. And the first thing we know is that H is admissible. H is admissible means H of n is less than or equal to H star of n. Okay. H star of n basically means the best path from n to goal, and best path from n to goal would be n to g obviously. Now, let us add g n on both sides. So, we can say that g n plus h n is less than or equal to g n plus h star n, which basically means g n plus h n is what? F of n, right. And what is f of n? F of n is g n plus h n. So, we can replace that in the inequality. And now, let us look at g n plus h star of n. What is g n plus h star of n? G n plus h star of n is the optimal cost, it is the cost to g n and the optimal cost to g. Right. Now, if I know that the path to g is the shortest path, okay, this is the step, only one step is interesting here. The path to g is the shortest path. So, what is going to happen? G n plus h star n, which is the cost to n so far and the best cost to a goal, is going to be exactly this path's cost. Right? This is the optimal path. So, therefore, we can say that f of g, right, what was f of g? The cost of this path plus 0 is going to be exactly equal to the cost of this path up to n plus the optimal path from n down the line to g. So, then basically we can replace in the second equation, which is g n plus h n less than or equal to g n plus h star n, we can say that left hand side is nothing but f n and right hand side is nothing but f of g. So, basically we can say that f of n should be less than or equal to f of g. Now, what are the things that we know? We know that f of n is less than or equal to f of g and f of g is less than f of g2. That means f of n is less than f of g2. If f of n is less than f of g2, what should my A star algorithm have done? It should have expanded n, but it expanded g2, therefore, there is a contradiction. That is my proof. It is really a one slide proof. Okay? So, the intuition it is saying is because H is admissible, I am being optimistic for the future. So, whatever node looks better to me in the full path estimated length, once I expand this, I will always be staying under the optimal path, and so when I finally remove the goal, I would have found the optimal path, because every other path will have a higher f value and that higher f value would be lower than the optimal path length to the goal through that particular sub path, and therefore, I would have found the optimal. This intuition of optimism is extremely important, and it is going to come up again and again in variety of places, not necessarily in this course, but in all kinds of search algorithms. The idea that you should be optimistic is a great idea. Later we will have uncertainty, we will have probabilistic models, and there is a concept called optimism in the face of uncertainty. That if you can have a range from negative to positive and you are maximizing, take the positive as its value. That is going to help you in getting to the optimal path. So, this intuition that admissibility, optimism is awesome for search remains with you in a variety of search algorithms, and the proofs are sort of very similar, because once I find a solution, the solutions that I have ignored can be proven to be worse, because I was being optimistic throughout. Once I reach a real solution and this real solution is better than the others and others are optimistic, their solutions are going to be even worse, right. So, then what I have found is the best. Okay. So, I encourage you to think about this proof and also read up the proof for A star graph search for consistency, and you will get some intuition about how to prove these optimality for these search algorithms. So, what are the properties of A star? So, we will not worry about time and space, as I said, because time and space is going to be exponential. You will have to, if your heuristic is terrible, you in the worst case I can get really bad. And as I said, if you can prove theorems, right, like if your heuristic is so much worse than optimal, then your time complexity can be better. In fact, it can even be polynomial if the divergence from the optimal heuristic is bounded by log of h star or something like that, and there are some proofs like that. So, you can check, but we will just not worry about it, we will say it is exponential. Now, when will A star not be complete? This is an interesting question. What needs to happen in my search space such that I get into some other territory and I never come out of it? I just never come out of it and I never find the goal. What needs to happen? I am expanding in F order. I have an optimal cost to the goal. What needs to happen? No, so we will not worry about negative values. Negative values is a whole another ball game completely, right. That let us just leave that for minor exams. So, essentially intuitively what is going on, I am always expanding the lowest F value node, and eventually when I expand goal I am done. What needs to happen that I can never expand goal? No, you are saying geometric progression, but what is geometric progression got to do with it? You have to say in terms of the properties of the algorithm. Yes. So, the suggestion is that in my frontier I always have suboptimal goals and all the costs for them are same, and you should always expand the lowest F value, and there will always be one of the nodes which lead to the optimal goal, and that will have lower F. So, you will expand that. We just proved this, right. What did we prove? That we will always have another node n which will lead me to the best solution, and its F value will be lower. So, we will expand that. So, that particular case is not possible. Yes, what is your name? Rajbir, yes. Okay, very good. So, the geometric progression idea comes back in, but the suggestion is that let us say my goal is at a distance 2.5, and let us say I have a sequence of nodes which have geometric progression of 1, then half, then 1 by 4, then 1 by 8. I will keep going, and let us say all of them have heuristic 0, which is admissible. Then what is going to happen? Eventually I will hit the goal? No, because its heuristic is higher, the F is higher, and I will have lots of nodes whose F value will be lower than the goal, but they are never finishing. So, what is the generalization of this? Geometric progression is one specific example, but I need infinite nodes of what? What should be the property of those infinite nodes? See, what am I using? I am using the F value. Their F value needs to be lower than which minimum value? So, we have the optimal cost path that we are looking for. Let us say that value is f of g. See, we are looking for a path of length f of g, the goal, the optimal goal. but we may not find that path if I have infinite nodes whose f value is less than that exactly. Okay. So, you will get some intuitions of this algorithm slowly, right, it takes time. So, you will have, if you have infinite many nodes with f less than equal to f of g, actually f less than f of g, well, that depends on how you do try breaking. So, let us just do f less than equal to f of g. So, if we have infinite nodes with f less than equal to f of g, then I will never get to goal, because I will keep adding them and I will keep expanding them and never get to the goal, right. And that is possible with this example of geometric progression, for example. So, if that does not happen, then at some point all the nodes which have value less than equal to f of g would have been expanded, and I will get to the goal node, and then it would be complete, right. Again, we are not talking about negative costs or 0 costs. Okay. And would it be optimal? We have already done. It will be optimal based on the heuristic property and the search property. So, tree search admissibility or graph search consistency. So, these are the properties of the algorithm. This is considered to be one of the most important algorithms traditionally, one of the most important search algorithms traditionally. The A star algorithm was developed as part of the Shaky project in Stanford, and it had far reaching consequences. And in fact, it is said that Bing's driving directions engine, Bing Travel, like Google Maps, we have Bing Maps, at least that I read a report about 10 years ago, was using some notion of hierarchical version of A star, and A star has been used extensively in a wide variety of algorithms and continues to be used. So, it is one of the algorithms from the 60s which is still as important as anything else, okay, in AI. And now, let us see how the run is when we try to go from the start state to the goal state. So, by the way, I should say that these beautiful videos are courtesy University of New Hampshire, and my good friend and colleague, or at least researcher colleague, Wheeler Rummel, whose student realized, and he is a well known expert in search algorithms. And notice, let us stop for a second. Notice how fast it is moving towards the goal. Now, if you remember from last class, depth first search would do completely random things, breadth first search will just go all around and look everywhere in the world, basically in all directions. Here, notice that I am giving it a heuristic function. The heuristic function is a straight line distance, right. So, notice how quickly it starts to go towards the goal. Now, you will be dissatisfied in the middle, and we will talk about why. So, let us see how this algorithm works. Now, are you a little dissatisfied at this point? What is the algorithm trying to do? Why is it searching for other paths on the right and so on and so forth when it feels as if it is so close to the goal? It knows it is very close to the goal. These points must have relatively less distance to the goal. Why is it not moving ahead? Because it also needs to prove, see, the G here is fairly high. The cost from this node to this node very close to the green dot is actually fairly high. So, it now needs to prove that there is no alternative path that takes me to the goal faster. So, it will keep proving those nodes suboptimal, and only when all the nodes other paths are looking worse, only then it will expand the right path. So, it will take some time. And notice now it sort of almost found the path, and it has now found the path, right. So, let us look at the final path that it found. Oh, I have to stop it at the right place in order to do that, right. So, now it found the path, it found the optimal path. Now, the beauty is, let us look at the beauty first. The beauty is imagine depth first search. It had expanded so much, and it had not expanded everything, of course, gone down a rut hole and finally came out from the wrong side and finally reached the goal. It had resulted in terrible paths. So, we do not want that kind of thing as our intelligence. We do not want the algorithm to just keep going, not the algorithm, the robot or any agent to just seemingly wander aimlessly and then finally randomly hit the goal. That is not very good. Breadth first search would have found the same path, but breadth first search would have expanded almost every node in the graph, and that was terrible because it was looking in all directions. It had no idea where the goal is. There was no notion of look ahead. There was no notion of estimates of the future. There was no understanding of the future. It was just blind. So, it was looking in all directions equally. Here the A star algorithm expanded a far less search space than breadth first search and still found the optimal solution. Now, of course, if you did greedy best first search and if it is not stuck in loops and so on and so forth, it would be even more goal directed. It will say you are closer to goal, I will go to you, you are closer to goal, I will go to you, with complete disregard on what has happened so far. So, it would expand even fewer nodes if it hits the goal, but it will not be guaranteed to be optimal, it will not be guaranteed to actually reach the goal. Okay? So, A star is a great balance between optimality and trying to use the heuristic function effectively. Oh, here is one important thing that I missed talking about. There is a heuristic function and there is a heuristic, and those two things are different things. When we use the word heuristic function, it is a very well defined theoretical concept. We are talking about the estimate of the node to a goal and so on. When I say it is a heuristic strategy, when I say it is a heuristic algorithm, when I say it is a heuristic, I am basically saying I can't prove much, but it is a nice trick to add in my algorithm. That is the notion of a heuristic. There is an intuition as to why I am adding it, but even if I do not have it, the algorithm might work. If I add it in practice, it might do much better, but I can't prove much here. That is the intuition of a heuristic. And do you know about HAL, like from the Space Odyssey? Do you guys watch science fiction? Do you know what HAL stands for? It stands for heuristic algorithmic. Some people thought that it stands for IBM because H is one letter less than I and A is one letter less than B and L is one letter less than M, but that was just a fluke. HAL in Space Odyssey had nothing to do with IBM. It stood for basically heuristic algorithms. So, in AI, as we like our theorems, we also like our heuristics. So, in the field of theory, heuristic may be a bad word. You would say, this fellow was not smart enough to prove anything, this fellow came up with a heuristic to make it work. But in AI, we are happy about our heuristics. We feel like if we added an insightful heuristic which made the algorithm go much faster in practice, even if we can't prove about it, great, awesome. Okay. But when we use the word heuristic function or heuristic in the context of A star, that is a different thing. There is a theory behind it, it has a particular meaning, it is an evaluation function of a sort. If it has certain property, we can prove things about it, etc., etc. So, that is a different. So, people confuse heuristic and heuristic function. So, I thought I will clear it. We can stop here. Thank you.